All right, thanks, Joyang. I'll get started now.
Yeah,
Hello, everyone. My name is Jerry Zhao, and I'll be presenting a talk on a new Chisel project I've been developing called Constellation, which, as Joyang described, is a Chisel generator for generating network on-chip interconnects. So first, a little about me. I'm a fourth-year PhD student at UC Berkeley, advised by Krista Sanovich. My primary interests have been in SoC architectures and high-performance CPU microarchitectures. And over the years, I've worked on a number of Chisel projects, most notably Chipyard, an open source framework for SoC design built on Chisel generators. And I've been the developer of Boom version 3, which is a Chisel generator for high performance, out of order RISC-V cores. So I want to start this talk by attempting to motivate the development of a NoC generator in Chisel. We see here a die shot of a relatively prominent SoC in the past 2 years, and I'm sure you've all heard about the Apple M1 SoC. Beyond the obvious performance and efficiency numbers, which Apple, of course, advertises, there's a couple interesting architectural features which I think is worth pointing out here. First is the level of heterogeneity present in the system. It's well known that big little architectures have significant advantages for performance and efficiency of constrained systems. And we see that design pattern here as well in the split between the performance cores and the efficiency cores in this design. In terms of specialized compute, we see even more tight integration with the GPUs and the MPUs. In the periphery of the system as well, there are dozens of even more specialized devices, including things like DSPs, audio encoders, and video encoders, and even more. And this heterogeneity extends beyond just the compute units of this SoC. It extends to memory as well. For main memory, we have distributed coherency across multiple L2s. We have multiple DRAM channels distributed across the periphery of the die. And we have different memory devices corresponding to various I/O sources, display input, display output, speakers, microphone, touch, PCIe, gyroscope, just to name a few. So it's clear that in a modern application class SoC, there's a high degree of heterogeneity involved in the architecture, both in compute and memory. Even more, based on an analysis of historical trends and historical designs of Apple SoCs, we expect this level of heterogeneity to only increase in the future. So for SoC architects, this naturally presents a challenge. And one of these challenges is, how do we engineer a system to support the on-chip communication patterns in such a complex heterogeneous device? The simplest solution, of course, has been to implement a shared bus or crossbar architecture for the on-chip interconnect. But while this approach is very simple to implement, it doesn't scale to a system with so many devices and so many cores and memory systems on it. The standard approach for scaling up an on-chip interconnect has been to build something called a network on chip, or a NoC. A NoC implements a network on the chip by implementing microarchitecture for router nodes of the network, which implement routing and passes packets through the network from node to the destination. And this increasing heterogeneity of modern SoCs, of course, presents new challenges to NoC design and motivates research into developing heterogeneous NoC architectures for these heterogeneous SoCs. Right. So to pursue this line of research into heterogeneous NoCs, we need open source NoC models or simulators. When we look at the landscape of what's available, we see some limitations here. So first of all, there's many open source NoC simulators available to just download and run. These are typically C++ models like BookSim or Garnet. And these generally support diverse NoC topologies and routing algorithms. But of course, they aren't real RTL. You can't implement these, and they don't provide any feedback on power or area of the implementation. There are, of course, a few open source NoC implementations. A couple are highlighted here are Open Celerity, the NoC in OpenPython, and ESP, and in MATLib. Generally, these are specific NoC instances that have been designed for one specific use case, whether it's a specific test chip or a specific framework. As a result, these NoC systems generally have fixed topology, fixed routing, and implement some custom chip-specific or framework-specific protocol, making it difficult to integrate custom blocks or explore custom communication protocols within these NoCs. And it's also generally been pretty difficult to parameterize these NoCs towards generating a more heterogeneous or irregular network topology. There do exist a few examples of NoC generators, however. A couple I'll point out are the OpenSoC Fabric and Connect. OpenSoC, notably, is also implemented in Chisel. So while these existing generators support a larger set of NoC topologies, the target use case has really been for fast FPGA-based emulation of NoC behaviors, not full system integration and evaluation in a complete SoC. Notably, without support for running a real coherence protocol, it's quite difficult to integrate this as the backbone interconnect in a real SoC. So what we're missing here is really a deeply parameterized NoC generator that supports prototyping of highly diverse and heterogeneous NoC architectures while still presenting standard interfaces for SoC integration. And so this is where Constellation fits in. Constellation aims to fill this gap by being a parameterized chisel generator for SoC interconnects, designed to be SoC capable while still being able to express a wide diversity of NoC architectures. It is designed to be a protocol-independent transport mechanism for a standard custom on-chip communication protocol, whether it's AXI, ACE, or TileLink, while additionally allowing the exploration of user-defined custom protocols and layering future custom protocols on top of the network. Constellation is, of course, highly parameterized, is capable of capturing highly diverse topologies, routing algorithms, and scales to networks with hundreds of nodes. Constellation is also correct and functional. It includes several mechanisms for ensuring that correctness properties of the emitted network are met, and I'll talk about these later. Constellation is also rather standard in its architecture and design. It generates a conventional baseline wormhole routed network with virtual channel flow control, making it useful for researchers studying what is a baseline implementation of a network on chip. And finally, Constellation is plug and play with existing Chisel projects. Specifically, it supports drop-in integration with Rocketship and Shipyard-based SoCs, replacing existing crossbar-based interconnects with a network-based interconnect. So now I want to talk a bit about how the Constellation flow operates. This diagram below depicts the flow, and I'll walk through this over the next few slides. Before I start, I think it's useful to go over the basics of how routing in a NoC behaves, as this should provide some background into how NoC operates and motivate some of the later design decisions. In a NoC, packet protocol messages are encoded as packets. A packet may be wider than the width of the network channels, so packets can be further decomposed into a sequential series of flits. Head and tail flits indicate the start and end of a packet, and the network endpoints packetize and reconstruct protocol messages. This packet flit format dictates the flow control implemented by the network. The standard in NoC implementations over the years, or in recent years, has been wormhole-based flow control with virtual channels. In this mechanism, flits in a packet follow each other through the network in a worm, allocating and deallocating buffer slots as they progress. We call these buffer slots virtual channels. So for example, we'll see here a 3-flit message being injected into a very simple network at router 0, and the destination of this packet is router 3. The way the network operates is that the head flit gets injected into the network and occupies some buffer slot. Now, note that even within a single router, there are often multiple buffer slots that a single flit can occupy. So what happens at routing is that the network has to decide what is the next buffer slot that this flit or this packet will traverse to. And there's a number of different options here, and the selection of the buffer slot will determine the path of this packet to the network. So in this case, flit 0 will move to this buffer slot, and the remaining flits in this packet will trail behind the head flit in a worm as the head flit sequentially repeats this process, allocating new buffer slots or virtual channels. And we see the trailing flits follow the head flit through the network. As the packet leaves the network, it deallocates those buffer slots and frees up resources for further packets in the network. So we observe from this mechanism that routing is really just a resource allocation policy. It's a policy describing how buffer slots or virtual channels are allocated to packets as they traverse this network. And this is actually a really useful abstraction to create, and this will actually inform the design of the rest of Constellation's parameterization system. So the first level, or the first stage in how Constellation operates, is we ask the user to specify what they want the network to be. In Constellation, there's 3 orthogonal component specification, or categories to the specification. There is the logical specification, which describes what logical flows the network is expected to handle, essentially the endpoint behaviors the NoC is expected to provide. Usually all-to-all traffic is necessary. Only a subset of potential flows are actually possible in a configuration. So the user will specify that here. And also importantly, at this level, we specify under what conditions the network must make forwards progress. This is important because when we layer a more complex protocol like AXI4 or tiling on top of the network, there can be situations where it is legal for an agent to block a channel or block a channel of the protocol while awaiting messages on another channel. The network must guarantee that in these cases, forwards progress is still possible. Notably, note that the logical specification does not provide any information on the underlying physical implementation of the network. It doesn't provide any information on the physical topology or how these messages are actually transported. That is the duty of one of the next layers of the specification system, which is the physical spec. This is where we actually describe the topology and the resources of the network. So what is the network graph? And what are the microarchitectural parameters of the routers and the channels within the network? How wide are the channels? How many buffer entries are in each channel? These types of parameters. And the final component of specification is the routing spec, which is the component which marries the logical spec to the physical spec. This is an allocation policy for physical resources to packets as they traverse through the network. So a user configuring Constellation can freely set the logical specification, physical specification, and routing specification all independently. And these are all just Scala data structures. So the logical specification is a list of supported flows. The physical specification is a Scala representation of a directed graph. And the routing specification is a function the user provides, which describes the conditions under which a packet is allowed to allocate a given virtual channel. So after the user provides all these specification components, the next step in Constellation is parameter validation. In this step, a abstract channel dependency graph of the NoC is constructed, and Constellation implements various graph analyses passes to verify that important properties or requested properties of the network are met on this graph. So purely from a Scala representation of the NoC, we can deduce several properties of the network, such as can all packets reach their destinations? Are there deadlocks induced by circular dependencies? And are there any deadlocks induced by protocol dependencies? These may seem like various relatively simple properties to meet, but this is really the heart at the heart of NoC design, and where a lot of the complexity in coming up with the routing algorithms and microarchitecture of the NoC comes from. So after parameter validation, the next step is actually generating the Chisel or generating the RTL for the network. Note that up till now, everything has been pure Scala, and only now do we actually pass the Scala parameters to the Chisel RTL generators. The RTL generators themselves are fairly conventional. They generate a pretty basic 4-hop router microarchitecture, although it can be configured to a more aggressive 2-hop router. Notably, the router generator is fully parameterized and it can support generating a router of arbitrary radix, implementing an arbitrary routing policy. We do this by leveraging the Espresso tool support in Chisel 3, where we can use Espresso to generate an efficient routing table within each of these routers. So after we generate the routers, the resulting Verilog implements a complete NoC with a minimal internal protocol. At the ingress points, flits specify whether they are the head, tail, or body of a packet, and also provide information on the destination identifier of the packet. So where is this packet actually trying to exit the NoC? At the egress points of the NoC, the NoC provides the head, tail information as before, as well as the ingress information of the packet. Thus, at the egress, enough information is provided such that the packet recipient can determine what the source of the message was. Note that the ingress and egress identifiers are not the same as the actual physical node index within the topology. The NoC internally will convert this user-provided ingress or egress identifier into an internal topology identifier to abstract away the physical implementation of topology from the endpoint behavior of the network. This makes it much easier to write test harnesses for the network because those test harnesses do not need to know anything about the internal network topology. And to demonstrate this, we can provide a simple traffic generator framework as part of Constellation to allow for evaluation of the NoC independent of any real devices. The user specifies a traffic pattern for the network, or can use a trace-driven traffic injector to describe what types of flows and the bandwidth and latencies of various flows that traverse the network. Since real networks don't experience uniform load across all the potential links, this system lets the user configure this independent evaluation to approximately match what the real network how the real network would behave when integrated into a complete SoC. Furthermore, the interface for this evaluation system is deliberately similar to existing NoC models like BookSim, making it familiar and easy to use for NoC researchers. And after running this framework, the traffic injection framework will measure things like packet latency and bandwidth and provide statistics on the behavior of the network under some given load. Of course, to attach a real device to the network, we must make the network capable of transporting a real protocol. To do this, Constellation implements examples of protocol adapters for TileLink and AXI4. The protocol adapters contain several components. The direct translation layer converts the protocol message to and from the NoC simple packet interface, and then the node adapter layer presents a shared ingress and egress pair as a single protocol master or slave. That layer also implements the address map for the system, which converts a protocol address to the destination identifier. This layering is designed to very carefully in order to preserve abstraction layers across boundaries. So the NoC implementation itself does not need to know how the address map maps onto managers and clients. The final level of layering here is diplomacy. So for integration to existing Chisel projects, we wrap all of the previous components into diplomatic nodes. So for those unfamiliar, diplomacy is another Chisel interconnect framework for describing directed acyclic interconnects. Because diplomacy is designed for acyclic interconnects, it actually cannot be used to describe a full network. But in existing projects which use diplomacy, the interconnect is usually implemented as a fully connected crossbar. And we can do a drop-in replacement, replacing the crossbar with this network-based interconnect. So this is really useful for us because a lot of projects use Rocketship, and this makes Constellation compatible with all of those with some minor tweaks. Before I move on to use cases of Constellation, I want to discuss some of the takeaways from implementing the system, because I think it might be of particular interest to the Chisel community. So some takeaways I had, compared to a core, a NoC is relatively much easier to implement. Design space is much more well-defined, and the generators are much more reusable. Constellation showed signs of life after only 2 weeks implementation, after only 1,000 lines of Chisel. And you can see the pie chart on the right breaks down lines of code of various components of Constellation. And you can see that only a relatively small portion of Constellation, like 30% or so, is the actual RTL for the Chisel generators. Everything else is the Scala for the configurations, the parameter validation, and a lot of code for the diplomacy adapters, of course. So because NoCs, I think, they need to be specialized for a given target SoC, and yet have a very large yet well-defined design space, I actually think that NoCs are a really good demonstrative use case of Chisel, demonstrating the usefulness of having very flexible parameterization of these generators. So finally, I think something else I realized from doing this project is that when writing a complex Chisel generator, you should really try to write Scala, not Chisel. What I mean by this is that you should try to maintain the design at a very abstract, easily manipulated level using Scala data structures, perform manipulations on these structures in the Scala space before concretizing the design using Chisel generators at the end. This is pretty speculative, but I would really like to see some sort of generalized framework for doing this kind of thing, where you have a framework where you run arbitrary passes, iteratively concretizing Scala data structures before finally passing the resulting configuration parameters to Chisel generators. This sounds very similar to diplomacy because it is. Perhaps this could be diplomacy version 2 or something. Right, so now that we've gone through the flow, I want to talk about 3 use cases which Constellation enables. Design space exploration of irregular NoC architectures, exploration of SoC architectures, and physical design of networks. For NoC design space exploration, Constellation enables simulation and full SoC evaluation of arbitrary heterogeneous NoC topologies. For example, we can take a heterogeneous SoC architecture with heterogeneous cores, GPU cores, banked memory I/O, and compare network topologies using a simple mesh and a complex hierarchical network. Traffic evaluation framework in Constellation lets us specify the expected traffic pattern for such a system and measure the latency and bandwidth for each of the network configurations under this expected traffic. Of course, we could also build this entire system and simulate it for precise numbers, or push the network through physical design to get area and power estimates. But using the built-in traffic evaluation framework lets you perform a first-order estimate of latency and bandwidth for these configurations. Constellation supports SoC architecture exploration as well. By being protocol independent, we can devise new protocols for on-chip communication, or even layer multiple independent protocols onto a shared interconnect. We can also explore multi-network SoCs. For example, there is some advantage in separating the control traffic of SoC from the application critical data traffic. Use cases, for example, a QoS or power monitoring core, which monitors SoC state through a narrow, low-cost control network without interfering with the performance critical traffic on the data network. We can implement such a system using Constellation and Shipyard. Finally, Constellation is useful for exploring physical design of SoCs and for education. In a recent course at Berkeley, 20 students used Constellation to generate the on-chip interconnect for a machine learning chip they taped out. They configured a 10-node network to manage on-chip traffic in a coherent multi-core SoC, and did this all in one semester, which was pretty impressive. This really demonstrates that Constellation is useful for, out of the box for people to use to generate a real RTL for a real network on chip that they might actually go on and implement in a tapeout. So to conclude, Constellation is a parameterized chisel generator of SoC interconnects. It unfortunately is not open source now. It's not open source yet. It will be in about 4 weeks in time for Micro. And there will be a demo and paper at Micro 22 as part of the Shipyard tutorial and NoC Arc workshop, respectively. I actually plan to open source it sooner, but I'm actually writing documentation for the system, and that takes a lot of time. So as soon as the documentation is done, and as soon as we can integrate this into Shipyard, it will be released. So stay tuned, and I hope to hear from you for any questions now. Thank you.